Welcome back to the Science Pillow. Tonight, we take a calm, deep journey to the very heart of our galaxy. Settle in. Make yourself comfortable. Dim the lights if they are not already dimmed. Let your breathing slow. Let the room grow softer at the edges. There is no hurry tonight. There is nowhere else to be. The voice will keep going. The journey will keep going. And the destination, the place we are quietly heading toward, has been waiting for billions of years. It will wait a few more hours. Tonight's destination is the most extreme place in our galaxy. It is the gravitational anchor at the center of the Milky Way. It is the engine that holds 300 billion stars in their long, slow orbits. It is older than the planets. It is older than the Sun. And, until very recently, no one had ever seen it. Its name is Sagittarius A Star, written as Sagittarius A, with a small asterisk after the letter A. Astronomers say A star out loud, almost like a single word. The asterisk is a small piece of borrowed language. It comes from atomic physics, where it marks an excited state, a place where energy is higher than expected. So, the name itself is a kind of warning. There is something here, something agitated, something more than the calm dust around it. Sagittarius A Star is the bright, restless point embedded inside a much larger radio source called Sagittarius A. The larger source is a blurry, complicated region of gas and stars and ancient supernova remnants. Inside that region, almost lost in the noise, is the small bright object that defines the entire galaxy. And inside that small bright object, hidden behind 26,000 light-years of interstellar dust, is something that should not be possible. It is a black hole, a supermassive black hole, 4 million times heavier than our Sun, compressed into a region smaller than the orbit of Mercury. If you placed it where our Sun is, in the center of our solar system, it would not even reach the inner planets. It would sit, dark and silent, where the daylight used to be. And yet its gravity, from 26,000 light-years away, still organizes the spiral arms of our entire galaxy. That is what we will spend tonight thinking about. Slowly, calmly, with no diagrams and no charts and no pressure to remember any of it. The numbers will pass through you the way water passes through a slow river. Some will stay. Most will drift on. That is fine. Before we begin the long descent toward the center, there is something I would like to mention. This channel, the Science Pillow, is a quiet corner of the universe, made for nights exactly like this one. Long-form science narration designed to soften your evening, settle your thoughts, and guide you gently into sleep. If that is what you came here for, please consider subscribing. It costs nothing. It only takes a moment, and it allows me to keep building these long, slow journeys for you. There is a small button below the video, somewhere in the dark. You do not need to press it now. You do not need to open your eyes. You can do it any time. The journey will not stop. Now, let us begin. To find Sagittarius A Star, you have to look toward the constellation Sagittarius. For most of the northern hemisphere, that means looking south in summer after dark. The constellation itself looks a little like a teapot. The bright stars draw a low, simple shape near the southern horizon, and the spout of that teapot points almost exactly at the center of the galaxy. If you have ever seen the Milky Way as a faint, soft band of light arching across a dark sky, the brightest, thickest, most crowded part of that band is in Sagittarius. That is not a coincidence. That is where you are looking through the most stars at once. That is the direction of the galactic center. You are not looking at the center directly. You cannot see the center, not with human eyes, not with optical telescopes. The line of sight is blocked by enormous clouds of interstellar dust. The dust is fine, almost like smoke. Each tiny grain absorbs visible light. Stack enough of those grains across 26,000 light-years, and the center disappears. The starlight from the very heart of the galaxy is dimmed by a factor of about 10 trillion in the visible part of the spectrum. That is why no one ever saw the center with their eyes. It is not far enough away to be invisible. It is just hidden. But certain wavelengths can pass through the dust. Radio waves can. Infrared light can. X-rays can in their own way. So, although the center is invisible to you and to me, it has not been invisible to careful instruments. For nearly a century now, people have been listening to it, watching it, photographing it through the dust. And what they have found is the object we are traveling toward tonight. Let us pause for a moment and think about how far away that is. 26,000 light-years. A single light-year is a little less than 10 trillion kilometers. So 26,000 light-years is a number that does not really fit inside a human mind. The light reaching your eye tonight from the direction of the galactic center. The radio waves that the great dishes of the world are quietly listening to. Those signals left their source 26,000 years ago. They have been crossing the dark for that entire time. When that light started its journey, the last ice age was deepening. There were no cities. There was no writing. The painted caves of Chauvet were 6,000 years in the future. Mammoths were still walking across Europe, and a small hidden object at the center of our galaxy was already what it is now. It has barely changed in all that time. 26,000 years of starlight. That is the foreground of tonight's story. The signals we use to study Sagittarius A Star are old by human standards, but young by cosmic ones. They tell us how the center looked very recently, in cosmological terms. Almost up to date. Let us travel inward, slowly. Imagine a slow, wide journey from where you are right now. Outside your window, above the clouds, above the atmosphere, into low Earth orbit. Pause there for a moment, looking back at the planet, blue and small. Then keep going. Past the Moon, past Mars, past the asteroid belt, past Jupiter with its slow storms, past Saturn with its rings tilted just so, past Uranus and Neptune hanging in the distant cold, past Pluto, past the heliopause where the sun's wind ends and the galaxy begins. Now keep going. The sun is behind you, becoming a star. Smaller, smaller, smaller. After a few light hours, it is just a bright star. After a few light years, it is just one of many. Alpha Centauri is to your left. Sirius is below you. The constellations begin to deform as you move. The patterns we know, the ones we draw on star charts, only exist from Earth. Move a few hundred light years, and they begin to stretch. Move a few thousand, and they are gone. You are inside a flat, slow disk of stars now. The Milky Way has a structure. It is shaped like a thin pancake, with a small bulge at the center and 4 main spiral arms wrapped around the bulge. The disk is about 100,000 light-years across. The bulge at the center is about 10,000 light-years across. The arms are decorated with bright young stars, dust lanes, and pink star-forming regions. The disk is sprinkled with older, calmer stars. And inside the bulge, surrounded by some of the oldest stars in the galaxy, there is a smaller, denser region called the nuclear bulge. And inside the nuclear bulge, there is something denser still, called the central parsec. And inside the central parsec, there is the object we are going to. You are still moving inward. The stars become more crowded. Where you live, the typical distance between neighboring stars is about 4 light years. Out near the spiral arms, it is about 3 light years. In the bulge, it is less than 1 light year. And in the central parsec, it is much, much less than that. Stars there are packed so tightly that a sky there would be an avalanche of points of light. There would be no real night. There would be no real dark. You are entering the central parsec now. A parsec is a unit of distance, about 3 1/4 light years. The central parsec is the small region that holds about 10 million stars within a region not even 4 light years across. It is the densest stellar environment we know of in the galaxy. Among those 10 million stars, there are ordinary ones, old red dwarfs, aging giants, white dwarfs that have already cooled. There are also some surprising young stars, bright, blue, massive stars that were born in the last few million years. No one is quite sure how they formed so close to the center, in such a violent gravitational environment. The mystery has a name, the paradox of youth, and we will return to it later, gently when we are deeper inside. For now, keep moving inward. Past the young blue cluster called the central cluster. Past the swirling streams of gas that flow toward the very middle. Past the so-called mini-spiral, a small filamentary structure of ionized gas that traces fluid motion around the central object. Past a series of smaller and smaller circles of orbiting matter. And here, finally, you reach the smallest circle of all. A region barely larger than the inner solar system. A region in which the stars are not in random orbits, not in the sweep of the disk, not in the slow tide of the bulge. They are all orbiting one thing. They are all orbiting around a single, dark, invisible point. And that point is Sagittarius A Star. It does not glow, it does not have a surface, it does not have a temperature you could touch. It is a region of space where gravity has won completely. It is the boundary of a one-way region, the event horizon of a black hole, and inside that boundary, no light, no signal, no object, no information ever comes back out. Whatever falls in is gone forever, as far as the rest of the universe is concerned. That is what we will sit beside tonight. We will study it. We will travel around it. We will look at the stars that orbit it. We will trace the long, careful work that humans have done to find it, to measure it, and finally to photograph it. And we will think gently about what it has to do with you, with your sky, with your evenings, with the calm light that reaches you across 26,000 years. Tonight is laid out in 6 slow sections. We will move through them one at a time. The first section is this one. We are still in it. We are settling in. We are getting our bearings. We are letting the idea of the galactic center grow familiar. By the end of this section, you will know where Sagittarius A Star is, what it looks like from far away, and how strange the journey to it actually is. The second section will be about how we found it. Not how we discovered black holes in general, but how we discovered this one. The story begins with a man in New Jersey, listening to static in the middle of the Great Depression. It runs through the rise of radio astronomy, the careful naming of a small bright spot in 1974, and the long, patient work of 2 teams of astronomers who watched the same patch of sky for decades, photographing the same stars over and over, year after year, until the orbits became visible. That work led to a Nobel Prize in 2020. We will sit with that story for a while. It is a calm story. The third section will be about what Sagittarius A Star actually is, not as a name, but as an object. We will think about what it means for something to weigh 4 million times the mass of the Sun. We will think about the size of its event horizon, about a radius of around 12 million kilometers, smaller than the orbit of Mercury. We will think about its density, which is paradoxically less than the density of water. We will think about how a black hole this large could even form. And we will think, briefly, about why ours is so quiet compared to the supermassive black holes at the centers of other galaxies. Sagittarius A Star is on a strict diet. Most of the time, it is barely eating at all. The fourth section will be about the stars that orbit Sagittarius A Star. They are called the S stars, and they are some of the most interesting objects in modern astronomy. One of them, called S2, takes about 16 years to complete one orbit. At its closest approach to the black hole, it moves at almost 2% of the speed of light. When astronomers tracked S2 through its perihelion, they were able to test Einstein's general theory of relativity in a place no one had ever tested it before. Einstein passed every test. We will go through the experiments gently in plain language. There will be no equations. The fifth section will be about the photograph. In May of 2022, the Event Horizon Telescope collaboration, a network of radio dishes scattered across 6 continents, released the first picture of Sagittarius A Star. It showed a soft, donut-shaped ring of glowing matter, with a dark hole in the middle. That hole is the shadow of the event horizon. It is the closest thing to seeing a black hole that we have ever managed. The image is small, fuzzy, hard-won, and breathtaking. We will spend some time on how it was made. We will also spend time on the other recent observations that complete the picture. The polarized image from 2024, which showed magnetic field lines threading the disk. The flares that astronomers have watched flicker around the hole in X-rays and infrared light. The mysterious objects called G1, G2, and others that appear to be drifting toward the black hole and sometimes surviving close passes. The way Sagittarius A Star feeds, almost shyly, almost reluctantly. The sixth and final section will be about the long future, about what happens to Sagittarius A Star in 1,000,000 years, 1,000,000,000 years, 100 billion years, and beyond. About how it will eventually merge with the supermassive black hole at the center of the Andromeda galaxy, the one called M31 star. About what gravitational waves will pour out of that merger, and about how, even after every star in the universe has burned out and gone cold, the black holes will still be there. They will outlast the stars by an unthinkable margin. And then, slowly, gently, they too will evaporate. We will walk all the way to that calm, distant ending, and by then, you may already be asleep. You do not have to listen to all of it. You do not have to remember any of it. Tonight is not a class. Tonight is a long road. You are walking it with me, but only as far as you want to. Take a slow breath in, let it out. Then another. Let your shoulders soften. Let your hands rest. Let your jaw unclench if it has been clenched. Let your eyes close if you would like to close them. We are entering the long part of the night. We are about to look back almost 100 years at the moment when the very first sign of the center of our galaxy, the very first faint whisper of Sagittarius A Star, was accidentally captured by a young engineer who was supposed to be studying telephone interference. He had no idea what he was hearing. He had no idea that the noise in his headphones would turn out to be the heartbeat of the Milky Way. Let us go and meet him. Section 2. Finding the Invisible. To begin, we have to step back a long way, almost 100 years, to a flat patch of land in central New Jersey, near a small place called Holmdel. The year is 1932. The world is in the middle of the Great Depression. People are walking past idle factories and quiet shops, looking for work that is not there. And in a field outside town, a young engineer named Karl Jansky is building a strange machine. Jansky is 26 years old. He works for Bell Telephone Laboratories. He has a thoughtful face and a serious posture. He wears a suit when he works, even outside. And he has been given an unusual assignment. The company that pays him wants to begin offering radio communication across the Atlantic Ocean. They are concerned about static. They want to know what kinds of natural radio noise might interfere with their signal. So, they have asked Jansky to build an antenna that can listen to short radio waves and to figure out where the noise is coming from. The antenna he built was huge by the standards of the time. It was about 30 meters long and 4 meters tall. It looked like a fence stretched across the field, made of brass tubing and wood with a turntable underneath. The turntable was mounted on the wheels of an old Ford Model T car, so the whole structure could rotate. People in town nicknamed it Jansky's merry-go-round. He could turn the entire antenna in any direction by pushing it gently. It would creak and roll and point itself at a different patch of sky. For months, Jansky listened. He wore headphones connected to the antenna's amplifier. He kept careful notes. He plotted what he heard hour by hour, day by day. Most of what he picked up was easy to understand. There was static from local thunderstorms. There was static from distant thunderstorms. There was static from electrical equipment. He learned to recognize each of these sources by their sound and their pattern. But there was a third source of noise that he could not account for. It was a soft, persistent hiss. It came from a particular direction in the sky. And the direction it came from did not stay still. It moved slowly across the day. At first, Jansky thought it was the sun. The hiss was loudest at certain times, and the sun moves, of course. But the timing was not quite right. The hiss did not return on a 24-hour cycle the way the sun does. It returned on a slightly shorter cycle. 23 hours and 56 minutes, almost exactly 4 minutes shorter than a solar day. If you have ever watched the stars, you may already know what that number is. 23 hours and 56 minutes is the length of the sidereal day. It is the time it takes for the Earth to rotate once relative to the distant stars, rather than relative to the sun. The sun rises a little later each day, by about 4 minutes, because the Earth has moved a small distance along its orbit during the day. The stars do not care about that motion. The stars come back at the same point in the sky, exactly 23 hours and 56 minutes after they were last in that position. Karl Jansky had built an antenna that listened to the radio sky. And what he had found was that one particular point in the radio sky was always loud. It rose and set with the stars. It was not a thunderstorm. It was not a city. It was not the sun. It was something out in space. Something steady. Something old. By 1933, he had narrowed down the direction. The hiss came from the constellation Sagittarius, the brightest part of the Milky Way, the part of the sky that, if our eyes could see radio waves, would shine very brightly indeed. Jansky had discovered the radio noise of the galactic center. He had no way of knowing, in 1932, what was actually producing it. He suspected, correctly, that it was the central region of the Milky Way. But he did not know about supermassive black holes. No one really did. The theoretical work that would predict them had barely begun. Albert Einstein's general relativity, which was the framework that allowed black holes to be a serious idea, was less than 20 years old. And the word black hole itself had not yet been coined. It would not appear in a published paper until the late 1960s. What Jansky did know was that something at the center of the galaxy was emitting radio waves continuously, day and night. He published his results in 1933. The work attracted attention. The New York Times put it on the front page. And then, like many things at the time, the world moved on. The Great Depression deepened. The Second World War began. Bell Labs assigned Jansky to other projects. He never returned to galactic radio astronomy. He died in 1950 at the age of 44 of a heart condition. He never lived to see what came of his work, but other people had read his paper. One of them was a young radio engineer in Illinois named Grota Reber. Reber was even more obsessed than Jansky had been. He built a parabolic radio dish in his own backyard in Wheaton, Illinois. The dish was 9 meters across. It looked like a satellite dish, but in 1937, no one knew what a satellite dish was. The neighbors wondered. Reber said nothing. Through the late 1930s and 1940s, Reber mapped the entire radio sky from his backyard. By hand. He drew radio contour maps that were the first of their kind. The galactic center was the brightest object in his maps. He confirmed Jansky's findings. He extended them. He showed that radio astronomy could become a real science. After the Second World War, the equipment of radar engineering became cheap. Teams of researchers began to build serious radio telescopes in England, in Australia, in the Netherlands, in the United States. The science of radio astronomy was born, and it grew quickly. By the 1950s, it was clear that the galactic center contained something unusual. It was very bright in radio waves. It contained a complex and confusing structure of hot gas, supernova remnants, and dense clouds. There was no single, simple object to point to. The whole region was loud. The whole region eventually got a name: Sagittarius A. The capital A meant it was the brightest discrete radio source in the constellation Sagittarius. There was a Sagittarius B, a Sagittarius C, and so on. The whole catalog of bright radio spots was numbered alphabetically, the way astronomers like to do. Sagittarius A was the loudest one in that constellation. It was also the broadest. It covered a region of about 30 light-years across. For a while, that was the state of the field. Sagittarius A existed. It was complicated. It contained gas and stars and the wreckage of old explosions. It might or might not contain something even more central. Theorists in the 1960s and 1970s began to speculate. Maybe there was a quasar at the center, in miniature. Maybe there was a giant black hole. Maybe there was a dense cluster of neutron stars. Maybe there was nothing in particular. The next big step was made in 1974. Two astronomers, Bruce Ballack and Robert Brown, were using a relatively new instrument called the Green Bank Interferometer in West Virginia. An interferometer is a way of combining the signals from several radio dishes to act like one big dish. It allows a telescope to see fine detail, much finer than any single dish could see. When Ballack and Brown looked at Sagittarius A with their interferometer, they saw something new. Buried inside the broad, fuzzy radio source, there was a small, very bright, very compact spot. The spot was less than 1/10 of 1 second of arc across. That is an absurdly small angle in the sky. To imagine it, you can think of the width of a human hair held at a distance of 50 meters. That is roughly 1/10 of a second of arc. The spot was that small, and yet it was producing as much radio energy as everything else in Sagittarius A combined. Balick and Brown did not know exactly what the spot was, but they knew it was important. They knew it was the core. They knew it deserved a name. And so they gave it one. They called it Sagittarius A Star. The asterisk was a reference to atomic physics, where it denotes an excited state, a state with extra energy. They wrote the symbol on paper as Sagittarius A with a small asterisk after it. People said it out loud as A Star. The name has stuck ever since. Sagittarius A Star was now an official object. It was very small. It was very bright. It was at the dynamical center of the galaxy. And nobody yet knew what was producing the radio light. It would take more than 30 years of careful, repetitive, patient work to find out. The next part of the story belongs to two scientists working on opposite sides of the Atlantic, almost in parallel. They each used different telescopes. They each built different teams. They each spent decades on the same single question. They sometimes competed. They sometimes cooperated. And in 2020, they shared the Nobel Prize in Physics for what they discovered together. The first is Reinhard Genzel. He is a German astrophysicist, born in 1952. He has a calm, intense manner of speaking. He likes to choose his words carefully. He spent the early part of his career working on infrared astronomy in California, and then in Germany, at the Max Planck Institute for Extraterrestrial Physics, in Garching, just outside Munich. The Max Planck Institute is a quiet, large, modern building. Inside, there are offices, computers, conference rooms, and a small kitchen with very good coffee. From the outside, you cannot tell that it has been one of the most important sites in modern astronomy. In the 1980s, Genzel began trying to take the highest resolution images he could of the very center of the galaxy. He used infrared light, because infrared can pass through the dust that blocks visible light. He used the European Southern Observatory's telescopes in Chile, on the Atacama Desert, where the air is thin and dry and steady. The conditions there are some of the best in the world for astronomy. Year after year, Genzel and his team photographed the central few seconds of arc of the Milky Way in the near infrared. They used a technique called speckle imaging, which captures very short exposures and combines them digitally to remove the blurring effect of Earth's atmosphere. Later, they began to use adaptive optics, which corrects for atmospheric turbulence in real time by deforming a small flexible mirror many times per second. With adaptive optics, Genzel's team could resolve details at the galactic center that nobody had ever seen before. They began to count individual stars. They gave each star a number. The brightest of them got short, simple labels: S1, S2, S4, S8, and so on. The S stood for Sagittarius. The numbers stood for the order of discovery. They watched the stars year by year. In the first year, the stars looked still. In the second year, the closest ones had moved a tiny bit. In the third year, the motions were unmistakable. The stars were orbiting something at the center, something invisible, something heavy. Across the Atlantic, in California, a second team was doing almost exactly the same work. The leader of that team was Andrea Ghez. She was an American astronomer born in 1965. She had grown up in New York City, fascinated by space since she was a child. She had completed her doctorate at Caltech. She had become a professor at the University of California, Los Angeles, while still in her 20s, and she had access to the largest optical telescopes on Earth. The W.M. Keck Observatory is on top of Mauna Kea, on the Big Island of Hawaii. It sits at 4,200 meters above sea level, where the air is cold and thin. The two Keck telescopes are huge, with primary mirrors 10 meters across. Each mirror is made of 36 hexagonal segments, fitted together with extreme precision. Each telescope is housed in a white dome that opens at night. From a distance, the domes look like two great pearls on the side of a sleeping volcano. Ghez began using the Keck telescopes in the early 1990s with the same goal as Genzel. She wanted to photograph the galactic center in the infrared, repeatedly, year after year, with the highest possible resolution. She used adaptive optics on Keck. She did not know about Genzel's work for some years, and Genzel did not know much about hers. They were on different continents, using different telescopes, with different instruments and different teams. For more than a decade, both teams kept observing. The S stars kept moving. The orbits became visible, then unmistakable, then beautiful. By the early 2000s, it was clear that the closest of the S stars, called S2, had completed half of an orbit. Its motion drew an arc on the sky. At that point, a calculation became possible. If you watch a star orbiting around an unseen object, and you measure the size of the orbit, the speed of the star, and the period of the orbit, you can use Kepler's laws and Newton's law of gravity to calculate the mass of the unseen object. The math is straightforward, even for a school student. The hard part is getting the data. The teams had the data. They did the calculation. The unseen object had a mass of about 4 million times the mass of the Sun, and it sat inside a region smaller than the orbit of Mercury. There was only one kind of object known to physics that could be that heavy and that small: a black hole. A supermassive black hole, by far the closest one to Earth. The result was published in stages throughout the 2000s and 2010s. It was confirmed many times. By 2008, it was no longer a hypothesis, it was a measurement. Sagittarius A Star was the supermassive black hole at the center of our galaxy. There was no longer any reasonable doubt. In 2020, the Nobel Committee in Stockholm announced the year's prize in physics. Half of the prize went to Roger Penrose for his theoretical work on the formation of black holes from collapsing stars. The other half was shared between Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. Andrea Ghez became the fourth woman ever to win the Nobel Prize in physics. The decades of patient observation had been rewarded. There is something quietly beautiful about that work, about waiting, about taking the same picture of the same patch of sky year after year, about letting the universe move on its own slow schedule, about the kind of science that does not happen quickly, that cannot be rushed, that depends on doing the same thing again and again and again until something becomes visible. The S stars had been moving the whole time, of course. The stars were not waiting for anyone. They had been orbiting Sagittarius A Star for millions of years, long before there were people, long before there were telescopes. The orbits were always there. The teams just had to be patient enough to see them. Tonight, those orbits are easy to find. You can pull them up on a website. You can watch animations of the S stars sweeping around the unseen central object year by year in fast forward. The motion is real. The data is real. The black hole is real. None of that was obvious even 30 years ago. Now it is settled, like a number printed in a textbook. The next thing to talk about is what that black hole actually is. What does it mean for something to weigh 4 million suns? What is the shape of its boundary? What lives just outside it? What lives just inside it? What is happening as we speak in the small region around Sagittarius A Star, where the laws of physics get strange? But before that, take another slow breath. Let the names of the people fade gently. Karl Jansky, with his merry-go-round antenna in New Jersey. Grote Reber, mapping the radio sky from his backyard. Bruce Ballack and Robert Brown, naming a small bright spot in 1974. Reinhard Genzel, watching the same field for 30 years from a German institute. Andrea Ghez, on top of Mauna Kea, in the freezing Hawaiian night, taking infrared exposures one after the other. None of them are standing in front of you. None of them are asking you to remember anything. Their work is finished. Their result is in the world. You are just allowed to know about it now, if you would like to know about it. Let us walk slowly to the edge of the black hole itself. Section 3. 4 million suns. We are about to think about what a black hole is, not as a metaphor, not as a science fiction prop, but as a real thing, made out of mass and curved space. It is helpful to start gently. A black hole is a place where gravity has won. It is a region of space in which the gravitational pull is so strong that nothing inside it can escape. Not a rocket, not a beam of light, not a single photon. Once something crosses the boundary, the rest of the universe loses contact with it forever. From the outside, the boundary is a perfectly black sphere. There is no surface, no light, no signal. There is only the shape of the region, defined by where light can no longer make it back out. The boundary has a name. It is called the event horizon. The word horizon is well chosen. From the outside, you can never see past it. Anything that happens beyond the event horizon, anything that falls in, anything that breaks apart, anything that decays, is invisible to you. No future event inside that horizon will ever be visible to anyone on the outside. That is what the word horizon means here. It is the edge of what can never be known from the outside. For Sagittarius A Star, the event horizon is a sphere of a particular radius. The radius is given by a simple formula that comes from Albert Einstein's general relativity. The formula was first written down in 1916 by a German physicist named Karl Schwarzschild, while he was serving in the German army on the Russian front during the First World War. He found the formula in a few weeks of work while suffering from a painful skin disease. He died not long after. The formula survived him. The Schwarzschild radius is proportional to mass. For every solar mass of black hole, the Schwarzschild radius is about 3 kilometers. That is, a black hole the mass of the Sun would have an event horizon 3 kilometers across. If you doubled the mass, you would double the radius. If you multiplied the mass by 1,000,000, you would multiply the radius by 1,000,000. It is a simple linear relationship. Sagittarius A Star has about 4 million solar masses, so its Schwarzschild radius is about 4 million times 3 kilometers, which is around 12 million kilometers. Some sources give the number as about 11.8 million kilometers, depending on the exact mass assumed. Either way, it is roughly 12 million kilometers across the radius. The event horizon is therefore a sphere about 24 million kilometers in diameter. 24 million kilometers. Let us think about that for a moment. The Sun is about 1,400,000 kilometers across. So the event horizon of Sagittarius A Star is about 17 suns wide. A row of 17 suns lined up edge to edge would just span the diameter of the event horizon. That sounds large, but it is much smaller than you might expect for a 4 million solar mass object. The orbit of Mercury, the innermost planet in our solar system, has a radius of about 58 million kilometers at its closest point. So, the event horizon of Sagittarius A Star is much smaller than the orbit of Mercury. If you placed Sagittarius A Star where the Sun is now and removed the Sun, then Mercury would orbit safely outside the event horizon. The black hole would still exert tremendous gravity. The orbit of Mercury would be very different. But the planet itself would not be inside the hole. It would still be in our world. This is one of the strange things about supermassive black holes. They are heavy. They are also relatively small. Even the largest black hole anyone has ever weighed, an object called Ton 618, with about 66 billion solar masses, has an event horizon that is only about as wide as 40 times the orbit of Pluto. From cosmological distances, that is nothing. From a human perspective, it is enormous. But still, the matter is concentrated into a region that is, by galactic standards, a single point. Now, let us think about density. Density is mass divided by volume. If you take the mass of Sagittarius A Star, 4 million suns, and divide by the volume of a sphere with the Schwarzschild radius, you get a surprisingly small number, about 1 ton per cubic meter. That is a little heavier than water. It is much less dense than rock. It is much less dense than the air inside a normal star. This is one of the most counterintuitive facts about supermassive black holes. They are not, on average, dense. The density of the object inside the event horizon, considered as a whole sphere, can be lower than the density of liquid water. The reason is that the event horizon grows linearly with mass, but the volume grows with the cube of the radius. So, as black holes get more massive, they get less dense, on average, even as their gravity gets stronger and stronger. Of course, this is the average density across the whole Schwarzschild sphere. The matter inside is not actually distributed evenly. According to general relativity, all the matter that has ever fallen into a black hole is concentrated at a single tiny point in the center, called the singularity. The singularity has zero size and infinite density in the equations. Most physicists do not believe the singularity is physically real. Most believe that some unknown quantum theory of gravity will eventually replace the singularity with a small but finite object. But until that theory exists, the singularity is what general relativity says is at the center. We will not focus on the singularity tonight. It is hidden behind the event horizon, far from anything we can ever observe, governed by physics we do not fully understand. We will stay outside. Just outside the event horizon, there is a region called the photon sphere. It is at 1.5 times the Schwarzschild radius. The photon sphere is the place where gravity is so strong that light, traveling in a straight line, bends around the black hole in a complete circle. A photon traveling exactly in the photon sphere can, in theory, orbit the black hole forever. In practice, the photon sphere is unstable. A tiny perturbation will send a photon either spiraling in or escaping outward. But it is a real boundary, with real physical consequences. We will return to the photon sphere when we talk about the photograph of Sagittarius A Star, because the photograph essentially shows the photon ring, which is the visible consequence of the photon sphere. Outside the photon sphere, there is another important boundary. It is called the static limit. Inside the static limit, an outside observer cannot remain stationary, no matter how hard their rocket engines push. The space itself is being dragged around the black hole, like a slow whirlpool. The region between the static limit and the event horizon is called the ergosphere. In the ergosphere, you must move with the rotation of the black hole, or you cannot stay still. The ergosphere only exists for rotating black holes. Sagittarius A Star is rotating, although the exact rate is hard to measure. It is probably rotating at a moderate fraction of the maximum allowed rate. A black hole that rotates at the maximum rate is called extremal. Sagittarius A Star is probably not extremal, but it is not zero either. It has an ergosphere, and that ergosphere is a strange place. Inside the ergosphere, you can extract energy from the black hole. This is a process first identified by the British physicist Roger Penrose, the same Penrose who shared the 2020 Nobel Prize. Penrose showed that if you drop an object into the ergosphere and let it split into two pieces, and arrange for one piece to fall into the event horizon while the other piece flies out, the escaping piece can carry away more energy than the original object had. That extra energy comes from the rotational energy of the black hole itself. The black hole spins down, very slightly. The escaping particle gains the difference. The Penrose process is one of the rare examples of a way that you could, in principle, mine a black hole for energy. We are getting deep into the physics. Let us pause and breathe for a moment. This is the Science Pillow, and it is good to remember that no one is testing you tonight. None of the numbers are required reading. It is enough simply to let them pass. The shape of the event horizon, the radius of the photon sphere, the slow drag of the ergosphere. They do not need to be remembered. They are part of the texture of the night. If you are still awake and the channel is helping you settle into sleep, I would mention again, very softly, that subscribing makes a real difference. It tells the algorithm that long, slow science narrations like this one have an audience. It allows me to keep recording new ones, week by week. There is no rush. You can subscribe whenever you would like. The video will keep going. Your evening will keep being your own. Let us continue. We have covered the geometry around Sagittarius A Star. Now, let us think about how we know its mass so precisely. The mass measurement is one of the cleanest in astronomy. It comes almost entirely from watching the orbits of the S stars. When a small object orbits a massive central object, the orbit obeys Kepler's laws. The first law says the orbit is an ellipse, with the central object at one focus. The second law says the orbiting object moves faster when it is closer to the center. The third law says the square of the orbital period is proportional to the cube of the orbital semi-major axis, divided by the central mass. If you measure the period and the size of the orbit, you can solve for the central mass. There's nothing else to know. For S2, the closest well-tracked star, the orbital period is about 16 years, and the semi-major axis is about 1,000 astronomical units. An astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers. So 1,000 astronomical units is about 150 billion kilometers. That is the average separation between S2 and the central object. At its closest approach, called pericenter, S2 comes within about 120 astronomical units of the center. At its farthest, called apocenter, it is about 2,000 astronomical units away. The orbit is highly elliptical. Plug those numbers into Kepler's third law, and the central mass comes out to about 4 million solar masses. The same answer is obtained from many other S stars with different orbits. They all agree. They all imply the same central mass. That is how the mass is known so well. Furthermore, the size of the central object can be bounded by the closest approach of the stars. S2 comes within about 120 astronomical units of the center. That is an upper bound on the size of the central object. Anything bigger than that, and S2 would have collided with it. There are now several stars that have been tracked closer than S2, and one of them, called S4716, has an orbital period of only 4 years. It comes within about 90 astronomical units. The central object must be smaller than that, so the central object is at least 4 million solar masses, and at most about 90 astronomical units across. That density is so high that there's only one known kind of object in the universe that fits the description: a supermassive black hole. The case is closed. Now, why is Sagittarius A Star 4 million solar masses, and not larger or smaller? This is one of the biggest open questions in astrophysics. The truthful answer is that we do not fully know. We do know from observations of other galaxies that almost every large galaxy contains a supermassive black hole at its center. The black hole's mass is loosely correlated with the mass of the galaxy's central bulge. For a galaxy like the Milky Way, with a bulge mass of about 10 billion solar masses, you might expect a central black hole of about 10 million solar masses. Sagittarius A Star is only 4 million solar masses. By that scaling, the Milky Way is somewhat underweight. Our central black hole is a little smaller than the average for galaxies our size. We do not know exactly why Sagittarius A Star is on the small side. Possibly it has had a relatively calm formation history, with few major mergers. Possibly the Milky Way's bulge, which is unusually small for a galaxy our size, is the relevant factor. Possibly the Milky Way is just on the lower edge of a wide statistical distribution. The full answer is unsettled. Astronomers are still working on it. What is the origin of Sagittarius A Star anyway? How does a 4 million solar mass black hole form? The honest answer is, we have several theories, and we are not yet sure which is right. One theory is that it began as a stellar mass black hole, the kind that forms when a single massive star ends its life in a supernova. Such a black hole is typically between 3 and 100 solar masses. Over time, the early stellar mass black hole could have grown by accreting gas and by merging with other smaller black holes, until it reached supermassive scales. This is the slow growth model. It works in principle, but for many of the largest supermassive black holes seen in the early universe, it works only with difficulty. Supermassive black holes have been observed at redshifts where the universe was less than 1 billion years old. To grow that large that fast, by slow accretion, requires a generous diet. A second theory is that supermassive black holes formed directly from the collapse of huge gas clouds in the early universe. This is the direct collapse model. In this picture, an enormous cloud of pure hydrogen, with very little ability to cool by itself, contracted under gravity into a single massive star, called a quasi-star. The quasi-star then collapsed directly into a black hole of perhaps 100,000 solar masses without ever shining as an ordinary star. From there, the seed black hole grew by accretion. Direct collapse is attractive because it gives supermassive black holes a head start. A third theory is that very dense clusters of small black holes in the centers of early galaxies, merged efficiently into a single big object. This is the cluster merger model. It is consistent with some simulations of the early universe. Whichever model is right, the result is the same. By the time the present-day Milky Way had taken shape, several billion years ago, Sagittarius A Star already existed. It has been there for a very long time. It has grown a little. It has nudged the orbits of some stars. It has occasionally consumed gas. But for most of cosmic history, it has been quiet. Compared to the brilliant accreting black holes in active galaxies like quasars, our central black hole is barely doing anything. That quietness is unusual, but not unique. Many galaxies have supermassive black holes that are mostly inactive. Most of the time, even an active black hole is quiet. The dramatic, brilliant feeding episodes happen rarely, and they last for a small fraction of the black hole's lifetime. Sagittarius A Star happens to be in a long, quiet period right now. It is not always going to be quiet. It has flared in the past. It will flare again. We will discuss those flares later. For now, picture our central black hole as a sleeping animal, curled up at the heart of the galaxy, breathing slowly. It is not asleep exactly. It is awake and aware. But it is not eating much. It is only nibbling at the occasional bit of gas that drifts close. It is thinking, in some very strange and abstract way, about its own enormous mass. And outside its event horizon, in the small space we call the central parsec, an entire community of stars goes about its long, slow life. The S stars orbit in their tight, fast loops. Other stars sweep through wider arcs. Gas streamers, ionized by hot young stars, snake around the galactic center in patterns that have been mapped in detail. There is even a small, recently discovered population of stars that may have been captured by the black hole long ago and that no longer come from anywhere outside the central region. This is the stage on which the next part of our story takes place. The S stars are not just data points for measuring mass. They are objects in their own right. They are some of the most extreme stars known. Some of them move at almost 2% of the speed of light. They get close enough to Sagittarius A Star that the laws of physics around them start to bend in ways that ordinary stars never experience. They have been used repeatedly to test Albert Einstein's general theory of relativity in a regime no one can reach in any laboratory on Earth. We will go meet them. Slowly, carefully, with time enough to look at each one. Section 4. The stars that refuse to stand still. Around Sagittarius A Star, there is a small swarm of stars. They are sometimes called the S cluster. The S stands for Sagittarius. The cluster is not particularly impressive at first glance. There are perhaps 50 stars in it, depending on how strictly you define the boundary. They are nothing like the spectacular open clusters or globular clusters that decorate the galaxy elsewhere. They are simply stars, ordinary by some measures, doing extraordinary things. What makes them extraordinary is what they orbit, and how fast they go. The S stars orbit Sagittarius A Star in tight, fast ellipses. The closest of them swing within a few hundred astronomical units of the central black hole at the bottom of their orbits. They reach speeds that, in ordinary stellar terms, would be absurd. They slow down at the top of their orbits. They speed up at the bottom. And then they begin the next loop. Each orbit is a small, fast meditation on the gravity of the central object. Among them, the most famous is S2. It is famous for several reasons. It was one of the first to be tracked over a full orbit. Its orbit is large enough to measure precisely, and small enough to traverse within the patience of human astronomers. It is bright, as such stars go, and it has been observed by both the Keck and Very Large Telescope teams for decades. S2 is a relatively young star by stellar standards. It is what astronomers call a B-type main sequence star. That means it is hotter than the Sun, more massive than the Sun, more luminous than the Sun, and it burns its hydrogen fuel much faster. It will not last as long as a Sun-like star will last, but while it lives, it is a clean, bright beacon, easy to follow on infrared images. S2 has a mass of about 15 solar masses. It is about 7 times wider than the Sun. It shines about 30,000 times brighter than the Sun in total light. If S2 were located where our Sun is, the Earth would be unrecognizable. The oceans would have boiled away long ago. The sky would be a furnace. But S2 is not at the center of the solar system. It is at the center of the galaxy, around 4 light hours from the central black hole at its closest approach, about 16 light days at its farthest. Its orbit traces a long, narrow ellipse around Sagittarius A Star, and the ellipse takes about 16 Earth years to complete. In the year 2002, S2 passed through perihelion, the closest point of its orbit. That was the first time astronomers had been able to watch a single star sweep through perihelion around the central black hole. They watched in detail. They were ready. At perihelion, S2 was about 120 astronomical units from Sagittarius A Star. That is roughly 4 times the distance between the Sun and Neptune. Compared to the rest of the galaxy, that is essentially a graze. S2 was practically inside the central black hole's atmosphere, if one could speak of an atmosphere for an object made of curved space. At that distance, the gravity of the central object pulled S2 forward at extraordinary speed. In the few weeks around perihelion, S2 was moving at about 5,000 kilometers per second. That is about 1.5% of the speed of light. A regular star doing 2% of the speed of light. Imagine that for a moment. The Sun moves at about 220 kilometers per second around the galactic center. S2, in the few weeks around perihelion, was moving 25 times faster than that. Such speeds are common for accelerated particles in laboratory experiments on Earth. They are not common for whole stars. You can stack atomic nuclei in a particle accelerator and push them up to those speeds. You cannot easily do the same to 15 solar masses of plasma. But the gravity of Sagittarius A Star is enough, and once you have a star moving that fast, in such an extreme gravitational environment, several relativistic effects become important. They are the effects that Einstein predicted in 1915. Effects that Newton's old theory of gravity does not include. They have been measured in less extreme conditions on Earth and around the Sun. The S-star measurements made it possible to test them in conditions much closer to those that exist near a black hole. 2 of those effects have now been clearly confirmed using S2. The first is gravitational redshift. According to Einstein, a beam of light climbing out of a deep gravitational well loses energy. The frequency of the light decreases. The wavelength becomes longer. In the visible part of the spectrum, this means the light shifts toward red. The deeper the well, the larger the redshift. Pulses of light from an atomic clock at the bottom of a well, climbing up to a clock at the top, are shifted by an amount that depends on the gravitational potential difference between the 2 points. When S2 was at perihelion in 2002, it was deep in the gravitational well of Sagittarius A Star. The light it emitted then had to climb out of that well to reach Earth. The light therefore arrived slightly more redshifted than it would have been at apocenter. The redshift is small. It corresponds to a few hundred kilometers per second of equivalent velocity. But the gravity collaboration, an international team using the Very Large Telescope Interferometer in Chile, measured it precisely during S2's next perihelion in 2018. The measurement matched Einstein's prediction. Newton's theory predicted no such redshift. Einstein won. The second effect is the precession of the orbit. According to Einstein, the orbit of a small object around a large mass does not close on itself the way Newton predicted. The ellipse rotates very slowly, so that the orientation of the long axis of the ellipse drifts forward each time the object completes an orbit. The drift is called Schwarzschild precession, after Karl Schwarzschild, the same Schwarzschild whose radius defines the event horizon. Schwarzschild precession is a real effect. It was first measured in the orbit of Mercury around the Sun in the early 20th century, and that measurement was one of the earliest confirmations of Einstein's theory. For Mercury, the precession is only a tiny number of seconds of arc per century. For S2, around a 4 million solar mass black hole, the precession is much larger. It amounts to about 12 minutes of arc per orbit. In 2020, the gravity collaboration announced that the precession of S2's orbit had been measured. The measurement matched Einstein's prediction. It did not match Newton. Once again, the older theory failed. The newer theory passed. These were not abstract experiments. They were photographs of a star, taken over decades by patient observers, processed carefully, fitted to mathematical models. The effects came out of the data with reasonable certainty. They confirmed, in the most extreme regime ever tested, the same theory that explains the slow drift of Mercury, the bending of starlight around the Sun, and the rate at which atomic clocks tick in airplanes versus on the ground. Albert Einstein died in 1955. He never lived to hear about the S stars. He never lived to see the gravity measurements. But every year, his theory passes another, harder test, in another, more difficult environment, and it keeps not breaking. This is unusual. Most theories in physics show their cracks under enough pressure. Einstein's theory of gravity is now over 100 years old, and it has yet to be definitively cracked anywhere. It is a remarkable piece of work. S2 is not the only S star. The list of well-known ones runs into dozens. They have names like S4, S8, S12, S38. Each one has its own orbit, its own period, its own ellipse, its own slow story. In recent years, several new S stars have been discovered with orbits even shorter than S2. The closer the star, the shorter the orbit by Kepler's third law. The very closest known stars to Sagittarius A Star are objects called S62, S4711, S4714, and S4716. Their orbital periods are around 3 to 4 years. Some of them get within about 90 astronomical units of the black hole at perihelion. They are moving even faster than S2 at their closest approach. S4714 has been measured at about 8% of the speed of light at pericenter, which is a record. These tiny, fast orbits are the most extreme stable orbits known to exist around any black hole. Closer in, the gravity becomes so strong that orbits become unstable, and any star would be pulled apart by tidal forces. The S stars are, in effect, the inner boundary of stellar life around Sagittarius A Star. Some of the S stars are odd in their own right. They are blue, hot, young stars, of a kind that should not be able to form near a supermassive black hole. The strong gravitational tides should disrupt any cloud of gas before it could collapse. There is a theory called the paradox of youth, which asks how such young stars exist so close to the central object. There are several proposed solutions. They might have formed in a denser, more shielded gas disk that briefly existed near the black hole. They might be the surviving inner cores of binary stars that were torn apart, with their outer companions ejected from the galaxy at very high speeds. They might be normal stars that were captured from a passing dwarf galaxy. The answer is not yet settled. This last possibility of being torn from a binary has a wonderful consequence. When a binary star approaches a supermassive black hole closely, the immense gravity can disrupt the pair. One member is captured into a tight orbit around the black hole. The other is flung outward at tremendous speed. The flung-out star can reach velocities high enough to escape the entire galaxy. These are called hypervelocity stars. They have been observed in the outer halo of the Milky Way, moving so fast that no normal mechanism can explain them. The most likely explanation is that they were once in binaries near Sagittarius A Star, and that the black hole gave them the kick that sent them into intergalactic space. They are still moving. Some of them will leave the galaxy entirely. You could think of Sagittarius A Star in this picture as an ancient gravitational sorting machine. It pulls in some stars. It throws others away. Its small region at the center of the galaxy has consequences that reach out to the very edges of the Milky Way. Returning to the cluster itself, the S stars are still there tonight. They are still orbiting. Even as you listen to this, SE2 is somewhere along its long ellipse. The next perihelion of S2 will be in 2034, 12 years after the last one. Astronomers are already preparing instruments for that perihelion. They expect even tighter measurements of relativistic effects. They hope, perhaps, to see deviations from Einstein's predictions. Perhaps a hint of new physics. Perhaps not. The other stars are also moving. S62, with its short period, is racing through perihelion roughly every 4 years. S4716 is making complete orbits roughly that often. The whole cluster, taken together, is doing something unique. It is performing a long, complicated, multi-body experiment about gravity in the strong field regime, and it is doing the experiment for free, with no human operating it. We are simply watching. It is good to know that those orbits are happening tonight, whether or not anyone is watching them, whether or not anyone is awake on Earth to track them. They will continue on their own schedules for many millions of years to come. They are perhaps the most reliably persistent ongoing experiment in the universe. Now we will move outward slightly, not back to Earth, not yet, but a step away from the close, fast S stars. Outward to the larger structures around Sagittarius A Star, the accretion of gas, the flares, the strange objects called G-clouds, and, eventually, the photograph that finally captured the shadow of the event horizon. For that, we have to think about light again, specifically the light that almost escapes Sagittarius A Star, the light that passes very close to the photon sphere, that bends around the black hole, that finally arrives at our telescopes after decades of travel. That light is what made the photograph possible. Take a slow breath. Settle deeper. The story is going to slow down a little in a good way. We have been moving fast through ideas. The next part will be quieter, and after that, we will sit for a long while with the photograph itself. Section 5. the photograph and the flares. For most of the 20th century, no one expected to ever see a photograph of a black hole. The reasoning was simple. Black holes are dark. They do not emit light. Any image of one would be by definition a picture of nothing. Even worse, the angular size of a stellar mass black hole, viewed from any plausible distance, was far too small to resolve with any telescope. But supermassive black holes are different. They are large, and they have hot, glowing material orbiting just outside their event horizons. The material is gas, accelerated by gravity, heated by friction, glowing brightly across the radio, infrared, and X-ray spectrum. If you could photograph that glowing gas at high enough resolution, you would see it form a ring around the dark central region. The dark region would be the shadow of the event horizon. The ring would be the photon ring, made of photons that bent around the black hole as they tried to escape. Some of those photons orbited the hole more than once before getting away. Their light makes the ring brighter and finer than you would otherwise expect. For a black hole as massive as Sagittarius A Star, located 26,000 light-years from Earth, the predicted angular size of the shadow is about 52 microarcseconds. That is 52 millionths of 1 second of arc. To imagine the size of a microarcsecond, consider this. A grapefruit on the surface of the Moon, viewed from Earth, has an angular size of about 1/4 of 1 second of arc. A pinprick on the surface of the Moon would be about 1 millionth of that. 52 microarcseconds is 100,000 times smaller than the apparent size of a grapefruit on the Moon. There was no telescope, in 2000, that could resolve 52 microarcseconds. There was no telescope that could even come close. The angular resolution of a telescope is, roughly, the wavelength of light divided by the diameter of the telescope. Smaller wavelengths give better resolution, but smaller wavelengths get absorbed by the atmosphere and by the dust in the galaxy. Larger telescopes also give better resolution, but no single telescope can be made large enough to resolve a 52 microarcsecond image. The dish would need to be, at minimum, thousands of kilometers across. The way around this problem is interferometry. If you have several telescopes, separated by long distances, you can combine their signals electronically to act, in some sense, as a single telescope with an effective diameter equal to the separation. This is called Very Long Baseline Interferometry, or VLBI. The angular resolution of a VLBI array is set by the longest baseline between any two of its telescopes. If you can build an interferometer that spans the entire diameter of the Earth, your effective telescope is 12,000 kilometers across. At a wavelength of about 1 1/3 millimeters, a telescope that big would have a resolution of about 20 microarcseconds. That is good enough to image Sagittarius A Star, just barely. The Event Horizon Telescope, or EHT, was the first project to seriously attempt this. It was conceived in the 1990s. It came together as a real collaboration in the 2000s. It involved radio telescopes scattered across the world, on 5 continents. By the mid-2000s, it included observatories in Hawaii, Mexico, Spain, Antarctica, the United States, and Chile. The flagship facility was the Atacama Large Millimeter Array in northern Chile, which by itself was an interferometer of more than 50 dishes. Combined with the others, the EHT became the largest telescope ever built. Its longest baseline was almost the diameter of the Earth. In April of 2017, the EHT carried out its first major observation campaign. The 8 participating telescopes were synchronized using extremely accurate atomic clocks. For several days, they all observed Sagittarius A Star and a few other targets simultaneously, recording the data onto huge arrays of disks. The disks were then physically shipped to 2 correlator centers, one in Bonn, Germany, and one in Cambridge, Massachusetts. There, the data from each pair of telescopes was correlated day by day, hour by hour, to extract the interference pattern that contained the image information. It was not a fast process. The total data volume from the 2017 campaign was several petabytes. A petabyte is 1,000,000 gigabytes. It took years to correlate, calibrate, and process all of it. The first image to emerge was not from Sagittarius A Star. It was from the supermassive black hole at the center of the galaxy M87, an enormous elliptical galaxy in the Virgo cluster. M87's black hole is about 1,000 times larger than Sagittarius A Star, but also about 2,000 times farther away. Its angular size is comparable, but it is much steadier. It does not change much from hour to hour. That made it easier to image. In April of 2019, the EHT collaboration announced the first picture of M87's black hole. The image was a soft orange ring with a dark hole in the middle. It looked, in retrospect, exactly the way the physicists had predicted. The shadow of the event horizon was clearly visible. The photon ring was clearly visible. The world saw, for the first time, an actual photograph of a black hole. That image became one of the most reproduced images in the history of science. It was on the front page of newspapers around the world. Sagittarius A Star was harder. It is closer, and it is much smaller, and that means the matter near it is moving much faster. The hot gas around our central black hole completes an orbit in minutes, while the gas around M87 takes days. That meant the EHT was effectively trying to take a long-exposure photograph of something that was visibly moving the whole time. It was as if you were trying to photograph a galloping horse with a slow film. The image would be smeared. The EHT collaboration worked on Sagittarius A Star for 3 more years. They developed new analysis methods. They modeled the rapid changes in the gas. They generated thousands of plausible images, fitted them to the data, and looked for the average behavior. They tested their methods against simulations. In May of 2022, they were finally ready. The collaboration held a coordinated press conference in cities around the world. They announced that the image was complete. They projected it onto the screen. It was beautiful. The image of Sagittarius A Star looks similar to the image of M87. There is a soft, glowing ring of orange-yellow light, with 3 brighter knots distributed around it. In the middle, there's a dark, round hole. The hole is the shadow of the event horizon. The ring is the photon ring, made of light that has been bent around the black hole on its way to us. The diameter of the ring is about 50 micro-arcseconds, exactly as predicted by general relativity for a black hole with a mass of 4 million solar masses. The image is not perfectly sharp. It has a soft, almost watercolor texture. That is partly because of the limited resolution of the EHT, and partly because of the rapid motion of the gas. The bright knots are not real features of the gas. They are likely artifacts of the way the EHT samples the sky, combined with the random structure of the gas at the moment of observation. Different reconstructions of the same data can produce slightly different patterns of knots. What is robust, what is the same in every reconstruction, is the ring itself, the shadow itself, and the size and shape of the boundary. It is one of the most direct images ever taken of an event horizon. It is also one of the most carefully tested. The EHT collaboration ran their data through dozens of independent algorithms, testing for biases and errors. The image survived every test. The shadow is real. The ring is real. The black hole is real, and we have its photograph. There was one further confirmation in the image, perhaps the most important one of all. For decades, even after the mass and the small size of the central object had been measured, there were a few stubborn theoretical alternatives to a black hole. Some physicists had proposed that the central object might be a so-called boson star, a hypothetical compact object made of bosonic dark matter, dense enough to mimic a black hole but lacking a true event horizon. Others had proposed even stranger objects, like Grava stars, with their own exotic surfaces. None of these alternatives had been ruled out by the orbits of the S stars alone, because the orbits could not probe deeply enough into the central region. The EHT image changed that. The size and the shape of the dark shadow in the photograph match, very precisely, the predictions of general relativity for a black hole of 4 million solar masses. They do not match boson stars. They do not match Grava stars. They do not match any of the alternative compact objects that have been seriously proposed. The simplest explanation, by far, is that the dark center of the image is indeed an event horizon. After almost 100 years of theoretical work and almost 90 years of observational hints, the case for a black hole at the center of our galaxy was now visually direct. The picture confirmed what the orbits had implied. The picture confirmed what general relativity had predicted. The picture did not leave much room for argument. In 2024, the EHT collaboration released a new image of Sagittarius A Star. This one was in polarized light. By measuring the polarization of the radio waves coming from the ring, the team could trace the magnetic field lines threading the gas. The polarized image showed a striking pattern of organized magnetic fields, similar to the pattern previously seen around M87. These fields are thought to play a key role in launching jets of energy from supermassive black holes. M87's black hole has a powerful jet that extends thousands of light years into space. Sagittarius A Star's jet, if there is one, is much weaker. But the magnetic field is there. The infrastructure is there. The black hole is geometrically configured the same way. It just is not very active right now. The reason it is not very active is interesting. Sagittarius A Star is, in technical terms, a very low luminosity active galactic nucleus. It eats almost nothing. Estimates of how much mass it accretes per year vary, but they are typically in the range of a few hundredths of an Earth mass per year. A few hundredths of an Earth mass. That is essentially nothing. By contrast, the supermassive black hole in M87 accretes thousands of Earth masses per year, and the brightest quasars in the universe accrete the equivalent of an entire sun-like star every few years. Why is Sagittarius A Star so quiet? We do not fully know. The most popular explanation is that the gas around it is very hot and very thin, almost a vacuum, with no efficient way to lose energy and fall in. The gas streams approach the black hole, swirl around it for a while, and then most of the gas is pushed back out by the energy released in the inner regions. Only a tiny fraction actually crosses the event horizon. Compared to the food it could be eating, Sagittarius A Star is on a near fast, but it is not always quiet. The gas around the central black hole can flicker and flare. Astronomers have been watching these flares for more than 2 decades. In X-rays, which probe the hottest gas, NASA's Chandra X-ray Observatory has watched Sagittarius A Star's emission rise and fall by factors of 10 or more on timescales of an hour. The flares are usually thought to come from compact regions of hot plasma, perhaps just a few times the size of the Earth, swirling close to the event horizon. They flicker. They peak. They subside. They are unpredictable but frequent. There is at least a moderate flare every day or two, and a strong flare every few months. In the infrared, the gravity collaboration has observed even faster flickering. In some flares, they can trace the motion of the flickering hotspot as it whirls around the black hole. The hotspot completes an orbit in less than an hour. Its motion is consistent with an orbit just outside the innermost stable circular orbit, a region only a few Schwarzschild radii from the event horizon. To watch a hotspot whirl that fast around a black hole that close to its horizon is a strange and special thing to see. Some flares are brighter than others. In April of 2019, Sagittarius A Star produced its brightest known infrared flare, exceeding all previous records by more than a factor of 2. No one knows what triggered it. The flare lasted about 2 hours. It is possible that some object had recently fallen toward the black hole and was now being shredded. It is possible that it was a normal flare that simply happened to be more intense than usual. The data is not conclusive. There are also longer-lived events on the scale of years and decades. In the early 2000s, astronomers began tracking an object called G2. It was a small, faint, infrared bright source approaching Sagittarius A Star at high speed. It was elongated with a long, thin tail. It looked like a small cloud of dust and gas. Its perihelion would happen in mid-2014 when it would graze the central black hole at a distance of only a few hundred astronomical units. The astronomy community waited eagerly. If G2 was a simple gas cloud, it was expected to be torn apart by tidal forces during perihelion. Some of the gas would fall onto the black hole. Sagittarius A Star might flare brightly. The whole event would be a spectacular natural experiment. When G2 actually went through perihelion, it did not behave the way a simple gas cloud should have behaved. It did not fully disrupt. Sagittarius A Star did not flare brightly. The post-perihelion images of G2 showed an object that had been somewhat stretched, but had largely held together. That suggested that G2 was not, in fact, a simple gas cloud. It was probably a star, surrounded by an extended envelope of gas and dust. The star at the center had held the system together. The envelope had been somewhat distorted, but had not been ripped away. Since then, more G objects have been discovered. They are now numbered G1 through G6 at last count. They all seem to be similar to G2. They are probably stars with extended dusty envelopes, perhaps formed by the merger of two stars in the chaotic environment near the black hole. They are local. They orbit Sagittarius A Star. They trace yet another aspect of the strange ecology of the central parsec. As time goes on, more of these objects will probably be found. Some of them, eventually, will be torn apart. Some of them will produce visible flares. The black hole will continue to feed lightly, mostly. It will continue to flicker and shimmer. It will continue to do so whether or not any of us are awake to watch. Right now, as you listen to this, somewhere on Earth, a radio dish is looking at Sagittarius A Star, probably the Atacama Large Millimeter Array in Chile, probably the Submillimeter Telescope on Mount Graham in Arizona, probably the IRAM 30-meter telescope in Spain, Probably the submillimeter array on Mauna Kea. Maybe several of them at once. They are not necessarily doing anything dramatic. They are just listening every day to the quiet hum of the galactic center. Some nights the hum is steady. Some nights there is a flare. Some nights an interesting structure shows up in some particular wavelength that no one has noticed before. In a slower, deeper way, this is what science feels like. Calm patience, long observation, occasional surprises. The galaxy keeps turning. The black hole keeps doing its quiet thing. The astronomers keep listening. They take notes. They write papers. They share their data. The picture slowly becomes clearer. We have gotten as close to Sagittarius A Star as we can get tonight. We have seen its photograph. We have seen its flares. We have heard the soft pattern of its breathing. There is no sharp boundary at which we have to step away. We could stay here, in the central parsec, for a long time, listening to the hum. But the night is not over. There is one more part to the journey. In the final section, we will turn around and look outward. We will think gently about the long future of Sagittarius A Star, about what happens to it in 1,000,000 years, in 1,000,000,000 years, in 100 billion years, about when it meets its bigger sibling at the center of the Andromeda galaxy, and about how, even after the stars are gone, it will continue to exist, shining only with the slowest, faintest light known to physics. Take a slow breath. The universe is not in a hurry. Neither are we. Section 6. A quiet giant in the long night tonight. Sagittarius A Star is doing very little. It is sitting at the center of the galaxy, eating almost nothing, holding 300 billion stars in their gentle orbits, accepting the occasional small meal of gas, occasionally flaring in the X-ray and the infrared. It is quiet by black hole standards. It is, we might even say, drowsy, but it has been there for a long time, and it will be there for much, much longer than any of us, or any of our descendants, or any of the things that will exist on Earth, or any of the stars currently visible in the night sky. Tonight, in this final section, we will travel through that long future, slowly, gently. Just as the night is winding down, the timescales we will use will grow longer and softer. By the time we finish, the universe itself will have grown unrecognizable. Let us begin in the near future, the next 1,000,000 years. In 1,000,000 years, the visible night sky from Earth will have changed somewhat. Some of the bright stars we use to guide ourselves will have moved noticeably. Sirius, the brightest star in the sky, will have drifted across the constellation. The Big Dipper will have warped into a slightly different shape. Some stars will have died in supernova explosions, and new ones will have lit up. But most of the constellations will still be recognizable. The Milky Way will still arch across the summer night the way it does now, and Sagittarius A Star will still be at the center of it, doing essentially the same thing it is doing tonight. 1,000,000 years is short by black hole standards. Sagittarius A Star will not have changed. Move out to 10,000,000 years. The arrangement of stars in the sky will be substantially different. Many of the constellations we recognize today will have dispersed. New patterns will have formed. The Sun, which is moving through the galaxy at about 220 kilometers per second, will have traveled about 7,000 light years. It will be in a different part of the spiral arm, surrounded by mostly different stars. It will still be a yellow main sequence star, much like today. Sagittarius A Star from this future sun will look essentially the same as it does now. It will still be located in the same direction in the galaxy. The galactic center will still be in Sagittarius, more or less. The S stars will be different, mostly, because their orbits are short and their numbers turn over. But the central black hole itself will have grown only by a tiny fraction of its mass, perhaps less than 1%. It is on a slow diet. Now move out to 100 million years. By this point, the Sun will have completed about half an orbit around the galactic center. The familiar shape of our galaxy will still exist. The spiral arms will still be there, although they will be in different places, threaded by different stars. Star formation will continue. Supernovae will continue. The slow turning of the Milky Way will continue. Sagittarius A Star, by now, will have grown a little more. Probably no more than a few percent. Still quiet. 1 billion years. This is where the picture starts to change. By 1 billion years from now, the Sun will have noticeably aged. It will be brighter than it is today by about 10%, as part of the slow main sequence brightening that happens as a Sun-like star ages. Earth, if it still exists in any form, will have an ocean's evaporated, runaway greenhouse climate. The biosphere we know will be gone. Perhaps something else, something engineered, something migrated, something resilient will live there. Perhaps not. We do not know. The galaxy itself, in 1 billion years, will be much the same. Spiral arms, bulge, disk, halo. But on the horizon, in the direction of the constellation we now call Andromeda, there will be a noticeable change. The Andromeda galaxy, which is currently about 2.5 million light-years from us, will have approached a great deal. Andromeda is moving toward the Milky Way at about 100 kilometers per second. In 1 billion years, it will be about 1 million light-years closer than it is now. It will be the largest, brightest galaxy in the night sky, easily visible to the naked eye, much larger and more striking than it is from Earth today. 2 billion years. 3 billion. The Andromeda galaxy continues to approach. It is no longer simply a smudge in the constellation. It is a tilted spiral, large and bright. The two galaxies, the Milky Way and Andromeda, are moving toward each other on a long, slow collision course. About 4 billion years from now, the two galaxies will begin to merge. Galaxies do not collide the way solid objects do. They are mostly empty space. The stars in two colliding galaxies almost never hit each other. The probability of a single star-on-star collision during a galactic merger is essentially 0. What happens, instead, is gravitational interaction. The stars do not strike each other. Their orbits get scrambled. Their gravitational potentials interfere. The clean spiral patterns dissolve. The disks become disrupted. Streams of stars get pulled out into long, graceful tidal tails. The shapes of both galaxies change. Eventually, the two galaxies merge into a single, fluffy, elliptical galaxy. It is sometimes called Milkomeda, other times Milkdromeda. The name has not been settled. Either way, it will be the new home of the stars currently in both galaxies. The merger will take some time. Several 100 million years, probably. There will be a long period of slow, complicated motions, with the two galaxies orbiting each other, passing through each other and rebounding. Each pass will scatter stars and tear gas. Each pass will trigger bursts of star formation, as gas clouds compress and ignite. Eventually, the two galactic cores, which are themselves dense centers of stars and dark matter, will sink together by dynamical friction. They will form a single core, and inside that single core, two supermassive black holes will be approaching each other. One of them is Sagittarius A Star, 4 million solar masses. the center of the old Milky Way. The other is M31 star, the supermassive black hole at the center of the Andromeda galaxy. It is bigger than Sagittarius A Star. Estimates place its mass at around 100 million solar masses, though there is some uncertainty. It is, as far as we can tell, similar in nature, just larger. It also has a small accretion flow. It also has its own community of S stars. It is also, generally, quiet. When the two galactic cores merge, the two black holes will end up in a binary system. They will orbit each other in a tight, slowly tightening pair. Their orbit will gradually shrink due to a mechanism called dynamical friction. As they orbit, they pull on the surrounding stars. The stars get flung outward. The black holes lose orbital energy. The orbit shrinks. Over millions of years, the orbit shrinks from light years across to light days across to light hours across. Eventually, when the orbit is small enough, a new mechanism takes over. The black holes begin to lose energy by emitting gravitational waves. Gravitational waves are ripples in the curvature of space-time, predicted by Einstein in 1916, and detected for the first time by the LIGO collaboration in 2015. Two orbiting black holes radiate gravitational waves continuously. The radiation carries away energy. The orbit shrinks. The radiation gets stronger. The orbit shrinks more. It is a runaway process. At the end, the two black holes spiral together at significant fractions of the speed of light, and they merge. The merger releases a tremendous burst of gravitational waves. For a brief moment, in gravitational wave brightness, the merging supermassive black holes outshine all the stars in the observable universe combined. The waves spread outward at the speed of light. Some of them, in some far future, will be detected by some far future observers, on some far future planet, or by some far future civilization. They will measure them, and they will work out what happened. They will understand that billions of years earlier, two galaxies merged, and at the center of the merged galaxy, two ancient supermassive black holes became one. The final, merged black hole will be larger than either of its parents. It will have most of their combined mass, minus the small fraction that was radiated away as gravitational waves. It will be on the order of 100 million solar masses, perhaps slightly larger. It will sit at the center of the new elliptical galaxy. It will continue to do, mostly, what supermassive black holes do. It will hold the galaxy together. It will eat occasionally. It will flare occasionally. It will be the heart of the new home for our descendants, if our descendants exist. That is the end of Sagittarius A Star as a separate object. After that, our central black hole is part of a larger one. Its name will change. Its identity will be subsumed into the merged galaxy. Some of its mass will continue, embedded in the new central object. Some will be radiated away. The rest will be the new heart of Milkomeda. But the universe will continue. It will continue much longer than the lifetime of any galaxy. Move forward to 100 billion years. By this point, the universe is much older than it is today. The stars that exist now, including the Sun, are long since gone. New stars have formed and died. The era of star formation is winding down because the gas in galaxies is being used up faster than new gas is arriving. There are still stars, but they are mostly small, slow, long-lived red dwarfs. The big, bright blue stars are extinct. The galactic disks have aged into smooth red glows. Move forward to 1 trillion years. The era of stars is essentially over. The last red dwarfs are burning out. The galaxies are dim, populated mostly by the cooling remnants of stars, white dwarfs slowly fading, neutron stars cooling, brown dwarfs that never quite ignited. The light of the galaxy is faint and reddening. The universe is dimming, but the supermassive black holes are still there. Sagittarius A Star, or rather, the merged remnant in which it now lives, is still at the center of the dimming galaxy. It does not need stars in order to exist. It does not need a galaxy in order to exist. It is its own gravitational object. It will outlast the stars by an enormous margin. Move forward to 10 to the 20th power years. By now, even the slow red dwarfs have all burned out. The universe is filled with cold, dark, quiet remnants. White dwarfs have cooled to the temperature of the cosmic background. Neutron stars have similarly cooled. Brown dwarfs have grown cold. There is essentially no thermal source of light anywhere. Galaxies are still gravitationally bound, mostly, although they have lost most of their gas, and many have shed their stars by gravitational interaction. But the supermassive black holes are still there. They are the most massive remaining objects in their galaxies. They sit, quiet and dark, at the center of dim halos of cold remnants. Move forward to 10 to the 30th year. The galaxies themselves have started to dissolve. Long-term, slow gravitational interactions cause stars and remnants to leak out of galaxies. The dispersal happens slowly, but inexorably. After 10 to the 30th years, most galaxies have evaporated, leaving their central supermassive black holes alone, with a small retinue of bound objects that did not quite escape. The supermassive black holes are now isolated objects, each one floating in a vast, dark sea, a long way from any other gravitational neighbor. Move forward to 10 to the 64th year. By now, the protons themselves, the building blocks of ordinary matter, may have decayed. Proton decay has not been observed in any laboratory, but many theoretical frameworks predict that it should happen on extremely long timescales. If protons have a lifetime of around 10 to the 34th years, then by 10 to the 64th years, essentially all ordinary matter has decayed away. The universe is now a thin gas of light particles, electrons, positrons, photons, and the supermassive black holes. The black holes still exist. They are now, by far, the most massive remaining objects in the universe. Each one is alone. Each one is dark. Each one is shedding only the slowest, faintest light known to physics. That faint light is called Hawking radiation, after the British physicist Stephen Hawking, who proposed it in 1974. Hawking showed that black holes are not perfectly dark. They emit a tiny, slow thermal radiation due to quantum effects at the event horizon. The radiation is incredibly faint for a black hole of any reasonable size. For Sagittarius A Star, the Hawking temperature is around 15 trillionths of a degree above absolute zero. That is colder than any laboratory has ever achieved. Colder than the cosmic microwave background. The black hole is, technically, glowing, but it is glowing at a temperature that is, for all practical purposes, nothing. Still, even nothing much, given enough time, adds up. Hawking radiation slowly carries energy away from the black hole. The black hole loses mass. A smaller mass means a smaller black hole, which means higher temperature, which means faster radiation. The effect is self-accelerating, but for a supermassive black hole of 4 million solar masses, the timescale is preposterous. Sagittarius A Star, as it currently is, would take roughly 10 to the 87th years to evaporate fully by Hawking radiation. That is a 1 followed by 87 zeros. a number that does not fit in any common unit, a number that dwarfs anything you have ever counted. But it is not infinity. Eventually, after that long, the last of Sagittarius A Star will be gone. There will be a final, faint pulse of Hawking radiation, as the last of the mass evaporates. After that, there is no longer any black hole at the position where Sagittarius A Star used to be. There is only empty space. There are only thin photons. There is only the cold, slow universe. By that time, the universe will be at almost its absolute temperature, near absolute zero. The cosmic microwave background, which today still has a temperature of about 3 degrees above absolute zero, will have cooled to almost nothing through cosmic expansion. There will be no stars. There will be no galaxies. There will be no planets. There will be no atoms. There will only be the cold, slow gas of the universe's eventual heat death. Sagittarius A Star is one of the very last things to disappear. The 4 million solar mass black hole at the center of our galaxy will outlast almost everything else in the universe. The largest black holes, like the ones at the centers of giant elliptical galaxies, will last even longer. But Sagittarius A Star is among the long-lived. It is one of the elders of the future. It will be there long after the sun is gone, long after the earth is gone, long after every star you have ever seen has burned out. That is a kind of immortality, not a perfect immortality. Even Sagittarius A Star will eventually, finally, evaporate. But on every human timescale, on every civilizational timescale, on almost every cosmological timescale, the answer is the same. Sagittarius A Star will still be there. Tonight, in the present moment, on a small planet in a quiet corner of one of the spiral arms, you are alive. You are listening to a calm voice tell you about a black hole at the center of your galaxy. The Earth is turning slowly underneath you. The stars are tracking quietly across the sky. The Milky Way is a soft band, somewhere out beyond your wall, beyond your roof, beyond your atmosphere. And Sagittarius A Star, 26,000 light-years away, is doing its quiet work. It is holding the galaxy together. It is barely eating. It is gently flickering. It is sending out long, slow, almost nothing radiation that will continue to be sent out for 10 to the 87th years. You do not need to know any of this. You did not need to know any of this. You can drift now. If you have made it this far, awake or half awake or quietly asleep, I am grateful that you spent the night with me. The Science Pillow exists because there are people, like you, who like long, slow, science narration to fall asleep to. Every subscriber tells the algorithm that there is room in the world for slow content, for soft voices, for 2-hour journeys through space and time. If you would like to subscribe, please do. There is a small button below the video. It will be there in the morning. The video will be in your history. You can find your way back any time. For now, though, settle deeper. Let the names fade. Karl Jansky, with his merry-go-round antenna in 1932. Bruce Ballack, in the basement of an observatory in West Virginia in 1974. Reinhard Genzel, in a German institute, watching the same patch of infrared sky for 30 years. Andrea Ghez, on top of Mauna Kea in the cold Hawaiian night. The Event Horizon Telescope collaboration, scattered across 6 continents, all of them looking up, all of them at once, in April of 2017. None of them are asking you to remember them. Their work is finished. Their results are in the world. You can drift. Let the geometry fade. The Schwarzschild radius, the photon sphere, the ergosphere, the event horizon. They are still there. They will be there in the morning. They do not need you to think about them. They are doing their own work, 26,000 light-years away. Let the stars fade. S2 on its 16-year ellipse. IS-62 on its short orbit. S4716 racing at 8% of the speed of light. The G objects drifting closer. The flares flickering in the X-ray and the infrared. The polarized magnetic field threading the disk. They are still there. They are still doing their slow, beautiful work. They do not need you to track them. Let the future fade. The Andromeda galaxy approaching at 100 kilometers per second. The eventual merger 4 billion years away. Milkomeda. The two black holes spiraling together. The gravitational wave burst. The quiet new center of the new galaxy. The long, slow stretch of the heat death. The Hawking radiation. The eventual, distant evaporation. They are all still there. They are all still happening somewhere on their own schedule. You are here right now. You are warm or you are nearly warm. The room is dim. The voice is soft. The galaxy is slow. The universe is patient. Sagittarius A Star is at the center of everything. It has been there for billions of years. It will be there for billions more. Tonight, it is barely eating. Tonight, it is barely awake. Tonight, it is doing essentially nothing. And in that nothing, there's a kind of peace that the rest of the universe is welcome to share. Sleep well. This has been the Science Pillow. Thank you for traveling slowly all the way to the center of the galaxy and back. There are many other long, calm journeys waiting for you on this channel. Black holes, distant galaxies, quiet planets, long-dead stars. Wherever you would like to go next, when you are next ready for a soft voice and a long story, I will be here. The button to subscribe is just below. The journeys will keep coming. There is no rush. For now, the room is yours. The night is yours. The stars are still tracking slowly across the sky. Sagittarius A Star is still holding the galaxy together, and you, here, are quietly, gently, drifting toward sleep. Good night.